So today we're gonna do an analysis of the heat equation using Fourier methods. We're just gonna use a typical kind of box function, which works as a multidimensional initial condition. And we're just gonna start in one dimension here. From -1 to 1. WR. So we're gonna use this function called heat Dirichlet, and we're gonna input our initial condition with the box and then put a time interval, and we're gonna visualize this as a surface. So this is the time evolution of the initial condition. We start with this box initial condition, and it diffuses according to the heat equation with Dirichlet boundary conditions. And if we'd like to test out what this looks like with Neumann boundary conditions, then we can just switch from Dirichlet to Neumann, and then the boundary conditions are now different. And similarly, there's a periodic boundary condition as well. And what's nice about this is that this can also generalize to higher dimensions using the programming language formalism I've developed for the Cartan package. So we're gonna set up a two-dimensional space. So this is the initial condition at time 0. And then as time, develops forward, it diffuses according to the Dirichlet boundary conditions. And alternatively, we can compare this with the Neumann boundary conditions. So there we can see that how the Neumann and Dirichlet boundary conditions would differ at time 0.1. And let's also look at the periodic one. Periodic. And we can try it in 3 dimensions as well. So we'll set up a XYZ space. And then So that's the initial box. And then we can see the tapering here is the time moves forward. So it still has kind of a cubical shape, but is rounded. And gets more and more round. Now it's quite circular and symmetrical. So that's some of the examples of the heat equation, and we can change the boundary condition, of course, as well. Let's start from 0.01 here. That begins interacting with the boundary. So there we go. We've done a little bit more partial differential equations here. This is the heat equation. We've got the different boundary conditions, Neumann, Dirichlet, and it works in any number of dimensions. And yeah, so that's with the Cartan package. If you're interested in this is discussed in my new textbook, Principal Differential Geometric Algebra. And yeah, so you can take a look at that. Principal Differential Geometric Algebra. Compute using Grassmann.jl and Cartan.jl is my new book. It's the first book I've written and published, and it's about the programming language things I've been working on. And there's a hardcover and a paperback version. It's 500 pages, with over 500 pages with many different scientifically reproducible diagrams and calculations, introducing people to the programming language paradigm that I've been working with, which is differential geometric algebra, and also some category theory at the beginning here. So yeah, this is a great textbook, new one that I've published. It's the hardcover version here. Got the back side here. So can read the back side here. Principal Differential Geometric Algebra is the first reference of its kind, built on rigorous category theory foundations and a full unified TensorField computational language design for differential geometry. This category theory foundation presented is a custom-designed formalism for categories to specifically emphasize the existence of choice morphisms, relevant to mathematicians interested in how the axiom of choice appears in class and set theory. Next, the book introduces essentials of geometric algebra as the primary basis for differential geometric algebra computational language design using Grassmann.jl library for the Julia language. Developed completely from scratch, Grassmann.jl introduced many pioneering computational language designs to enable reproducible scientific research with numerical differential geometric algebra. Building on Grassmann.jl, the Cartan package is the first computational language design to pioneer a FrameBundle for the PrincipalFiber G-bundle formalism used in advanced differential geometry. Not only does Cartan.jl present completely new programming paradigms for working with an abstract FiberBundle topology using numerical analysis, it also unifies the topological implementations of structured and unstructured finite element methods and also spectral element methods. This book emphasizes the analysis of eigen-characteristics with multilinear algebra, differential geometry, and partial differential equations. Many figures and diagrams are included, all scientifically reproducible with concise programming language. Partial differential equation examples are evaluated with boundary conditions found in the literature to help scientists and engineers validate the usefulness of the computational language design. Also included are many special and elliptic functions and appendices for basics of the Julia language, the Reduce.jl package, the Fatou.jl package, and also the new Unified System of Quantities for physics units from the UnitSystems.jl package. So this is the first edition from 2025 of my textbook, Principal Differential Geometric Algebra, compute using Grassmann.jl, Cartan.jl. So I'm excited about this new textbook. It's now available. Yes, so includes very much interesting information about differential geometry, partial differential equations, geometric algebra. Some category theory as well. So, yeah, I'd be interested to, get people's feedback about this. This is my first book. So, yeah, and if you buy this book, that helps fund my research project in the math and programming language design. So thank you very much for checking it out. It's my new textbook. Yeah, covers many different topics. Yep. Thank you for checking it out.
cross product of two things that are parallel is zero. So there's no force on a field-aligned current. So the superimposition of the circular component with the linear component, or an arbitrary angle of input of current, is, of course, circle plus straight lines healing. Now, why they form in pairs is not an easy question. They do. That's a laboratory finding. The little curve on the right just shows that if these things get too far apart, there seems to be a force that pull them back together. If they get too close together, there's a force that pushes them apart. Plasma forms cells and insulates regions